Okay, so we've covered an awful lot of ways of evaluating series. So when do we use them? All right, so for a geometric series, if it looks like our geometric setup, that we want it to be our number times something to a power. And this one, typo in here, it starts with a 1, should start at a 0. And then our conclusion, if it's our absolute value of r is less than 1, we have our nice equation. If it's greater than or equal to 1, it's going to diverge. The test for divergence, called it or divergence test, we call it test for divergence, same idea, is whenever we have our series, take the limit of our terms, see if it goes to 0. If it does not go to 0, diverges automatically. However, if it does go to 0, doesn't tell us anything. Might converge, might not. Next up, P series. If we have the 1 over something to the P, converges for P greater than 1, diverges for P less than 1 or equal to 1. Integral test. And we rewrite our integral so that it's a function that we can take the integral fairly easily. Keep in mind that this is an improper integral because it's going to infinity. If that integral converges, then our series will also converge. If the integral diverges, same thing with our series. Comparison test. Our function is doing something that it might not be easy to evaluate, but can we find something that's going to be similar to it? If the big one converges, small one converges. If the small one diverges, big one diverges. So we have to be very selective with our functions that we're choosing to do our comparison. And this is sometimes called direct comparison test. Limit comparison test, similar idea. How do these behave? Do they behave in similar ways? We'll take the limit of the ratio. Order does not matter in this case. We want it to equal to something that is bigger than 1, but less than infinity. And that's a follow the leader. Whatever the one we know how to handle, however that behaves, the other one's going to behave the same way. If we have that -1 to the n, or n plus 1, or n minus 1, whatever, where our other terms are all positive, because we don't want to have to alternate back and forth with two things with the sign changes. We got to be careful with that. We do two things. We have to make sure that our limit of our terms goes to 0 and that our terms are decreasing. Then it converges. For absolute convergence, if we can take an absolute value and it still converges, then the regular series is going to converge as well. With our ratio test, especially with exponentials or factorials, and then our root test, those who have exponentials, specifically if the whole thing is raised to a power, we're going to evaluate those the same way. But for our root test, or excuse me, ratio test, do the fraction, this is missing the absolute values. We need those absolute values in there. And it equals something. If it's less than 1, converge absolutely. Greater than 1 will diverge. And if it's equal to 1, inconclusive. Find another test. For our root test, the value here around the a sub n, do the limit of the nth root and see what happens. Same thing of less than 1, greater than 1, equal to 1. Now, to give a little better understanding of this, here is that same information again, but with a few examples and a few more notes. Again, test for divergence. This is something where you would notice, and I would do this first all the time. Check and see, hey, what's happening inside? What are my terms doing? Always check this first, because if it does not pass the test for divergence, this is usually your easiest way of handling it. P series again, comparisons with our p-series. Now, p-series isn't going to be used a whole lot just by itself. We usually don't get something that's going to be quite that easy, but it's often used with our direct comparison test or the limit comparison test. That we have another polynomial, kind of like what we have down here with our direct comparison test. All right, this is kind of hard to evaluate, but if we just had this part, the p-series, that's easy. So we know what's happening here. It's going to converge. Let's compare it to the other one. And usually we'll drop our sigma notation here, drop the summations when we're just doing this straight comparison. Then we can say something about the summations altogether. Similarly with this one, our small value here with the 1 over n is diverging. So something that's bigger will also diverge. Big thing converges, so the little thing is going to converge. Order makes a big difference for direct comparison tests, so be careful with that. Now, the limit comparison test, we have a little more freedom. Here, our direct comparison test would not work because the small thing is converging. Don't know anything about the big thing. Here, the big thing's diverging. Can't say anything about the small thing. But with a limit comparison test, this little bit of an order doesn't matter. So the limit comparison test is a bit more versatile than the direct comparison test. It's useful in a bit more situations. We don't need to care about the order and of which one's bigger, which one's smaller with our individual terms. We just have to take our limit and then make sure that our value is a finite number bigger than 0, and it's going to converge. If we get 0 or infinite, or well, excuse me, we want to get a number that is finite, that's not 0, and then it follows a leader of whatever the comparing series did, or the series that we used in our comparison did. That's going to be what's going to happen to our actual series. If we get 0 or infinity as a result of our limit, we messed up. We used the wrong comparison. Integral test, find something that's easy to integrate, like this one. We could also do this as a nice limit comparison test. But the integral works fairly nicely too. A little bit of u substitution, and then using your, again, improper integral. So you have to take a limit from 1 to n as n goes to infinity and evaluate it. So a little bit involved there. There's a little nuance, but fairly straightforward thing to do if it's an easily integrable function. Alternating series, having that -1 to the n or n plus 1 or n minus 1, that makes it stand out. Typically, we want to do this whenever we have nice polynomials. If you're going to have an exponential or a factorial, there are some other methods that we can use for that. But the -1 to the n is a big giveaway. Ratio test. We want to do not use it whenever you have polynomials or rational expressions, or at least only rational expressions. Make sure that you have factorials or exponentials in there somewhere. Like this one has a polynomial on the top, but it's an exponential as well. That's okay. This one has exponentials and factorials. Good example of when to use it. Root test, when the entire thing is raised to the nth power or something similar. Always all raised to a power, then I would use the root test. If it's a combination of something along these lines, doing an nth root of an n factorial, that's kind of tough. Doing nth root of an n, that's kind of difficult, so be careful. So big part of the strategy is recognizing which test you want to use. And lists can help, but practice will be even better. That the more you do these, the more you're going to come across different situations. And then the more you can then recognize, oh, I tried this, it did not work. But more importantly, you can see, okay, I tried this, it did not work, and here's why it didn't work. So it's a little bit stronger connection in your head than just, hey, do this and have a rote memorization type thing. When you are trying these and doing your practice problems, try different tests. See if you can make one work. Even though they expect you to do one thing or you're recommended to do one thing, try the others just to see what would happen. And then that can further ingrain in your mind why certain methods should be used in certain situations.